On with your second lecture.
All right, thank you very much. Just to briefly kind of put it all in the perspective, what we did last time. Last time I showed this slide, and I know I'm not full screen now, but I want to just kind of flash it real quick. The goal was to introduce you to sort of a classical, a quasi-classical small x physics and start small x evolution. And then today the goal was to finish small x evolution and talk about TMDs at small x. As usual, the goals turned out to be too ambitious. So in practice, what we covered last time was just the first third of the plan, just the classical small x physics. So today we're going to talk about nonlinear small x evolution. And realistically, I'll probably have no time to mention TMDs at small x. If I do have a few minutes, maybe I'll just kind of run through that section, just hitting the main points. And and the slides are posted on Slack and presumably on Indica by now. So if you want to kind of review them by yourselves, you're welcome to, or you could ask me questions by email later on if needed. Okay, so that's just a kind of a brief preview. This is where I wanted to start. This is a brief summary of what we covered last time. So we discussed a dipole picture of deep inelastic scattering that at small x, the dominant contribution to to deep inelastic scattering cross section and structure functions like F2 and FL comes from the dipole picture where the virtual photon emitted by a lepton splits into a quark-antiquark pair, and then that quark-antiquark pair, the dipole, travels through the target, shown here to be a nucleus. It could be just a proton. And in case of a nucleus, for instance, we also studied multiple interactions with multiple nucleons in the nucleus. I'll kind of remind you of that a little more in a minute. And then, of course, for total cross-section, you need the forward scattering amplitude, so the dipole has to merge back into a virtual photon. We discussed that you have a separation of time scale, that it takes a very long time for the photon to split into a QQ-bar pair. So that happens way before the collision. And therefore, it can be factorized, like those little vertical band lines denote kind of separation between the light cone wave function of the virtual photon splitting into QQ-bar pair. This is the same psi, and the dipole amplitude n, which describes the interaction of a quark-antiquark dipole with the target or nucleus. The light cone wave functions are known. It's just a QED process. The photon goes into quark-antiquark, could be even electron-positron pair, right? A very similar wave function you would get there. So these guys are known, psis are known, and all the QCD interactions are in the dipole amplitude. Dipole amplitude depends on the transverse size of the dipole. It depends on the impact parameter between the dipole, between the dipole and the nucleus, and it depends on the center of mass energy through this rapidity variable y, which you can think of as log of energy over some transverse momentum scale, or just log 1 over x. So QCD interactions are in this amplitude n. Sorry, was there a question or did I miss here? No? Okay. And the amplitude n interacts through multiple rescatterings. So we evaluated, the amplitude n in approximation in a simple multiple rescattering model where we have many nucleons in the nucleus, and with each nucleon we exchange just a pair of gluons. At the end of the day, we got this amplitude n plotted in this little plot in the middle right section. So n is a function of the dipole size, would go to 0. When the dipole size goes to 0, we discussed that this is the color transparency phenomenon. But when the dipole gets very large, there is a black disk limit, which translates into n equals 1. And this black disk limit has to be obeyed. It's a consequence of unitarity. So this amplitude actually, because of multiple rescatterings, obeys this limit. So from growing kind of quadratically with the size of the dipole, at larger dipole sizes, the amplitude would turn over and kind of saturates, quote unquote, at n equals 1. And this is a sort of the simplest example of saturation. We have something which grows and then eventually stops growing and reaches a limit, which is, in this case, a constant n equals 1 limit. And we also observed that the transition between this growth, quadratic growth with a dipole size, to this saturation regime happens at the sizes of the dipoles, which we can write as 1 over momentum scale, and this momentum scale is called QS. And we argued that QS for a nucleus, that was a nucleus example, a nucleus target example, for a nucleus, QS squared grows as a to the 1/3. So for large nuclei, it can be perturbatively large. Then 1 over QS would be perturbatively short, the distance. Lambda here is some infrared cutoff, right? Think of it as lambda QCD. So the non-perturbative physics resides up here, but the interesting transition into the saturation regime happens at still perturbatively short distances, where 1 over QS is small, and therefore alpha S is small as well. Finally, the last part of the talk yesterday, we talked about a different tack on much of the same physics called the Maclaurin-Venegopoulos model, where one could argue that if you have a very dense system like a large nucleus, which has lots of nucleons in it, nucleons have lots of gluons. So there's a lot of gluons in the nucleus, right? Just because the sheer number of nucleons multiplying the number of gluons by the atomic number A. This dense system, its gluon field is dominated by the classical gluon field. Classical gluon field one can calculate for a single nucleus. One can actually solve the classical Yang-Mills equations, find the field A mu of a single nucleus, and one can actually calculate the corresponding TMD, the so-called Weizsäcker-Williams gluon TMD, directly by calculating a correlation function of 2 of those classical fields. So the correlation function is pictured as a diagram on the right. Each of those structures is a non-abelian classical field, A perp, and then A perp correlation function gave us something in the small x community we call the unintegrated gluon distribution, but it's proportional to the gluon TMD, which I gave you a formula for. It has a similar this 1 minus exponential a structure that the dipole amplitude had. This is not entirely a coincidence, but I'm not going to go into more details here. What was important was this distribution. We saw that the majority of the gluons given by this gluon distributions, they have KT of the order of QS. So if QS again is perturbatively large, this is an interesting situation where majority of the gluons in the small x wave function of a large nucleus will have perturbatively large momentum, and therefore will be in a regime where we can do perturbative small coupling calculations. So that is sort of the advantage, and that was really where we started our whole discussion yesterday, that in saturation physics, we have this large scale QS, which justifies the use of perturbative small coupling calculations. Okay, so this is where we stopped last time. Any questions? Does anyone have any questions about any of these? No? Okay, if there are no questions, let's move on. So classical physics, this quasi-classical physics we discussed, it's wonderful, it's useful, but it cannot be the whole story. For once, there is no x dependence. Even though I'm writing this, say, distribution function, this Weizsäcker-Williams TMD as a function of x, nowhere on the right-hand side there is x dependence. There is x perp, but that's just the size of the dipole, and it's an integration variable. Saturation scale here scales with QS square scales with the size of the nucleus A, but there is no x dependence in the saturation scale at this point. So this classical picture is wonderful, but really has no x dependence, and that cannot be the whole story, right? We know observables depend on Bjorken X, they depend on center of mass energy, right? Cross sections, hadronic cross sections tend to grow with energy. Structure functions grow at very small x very fast. So do PDFs. This is a nice model, but it cannot be the whole story. So to remedy this and bring in x dependence, one needs to study small x evolution equations, and that's the next topic we're gonna tackle. So first, sort of a bird's eye view. This is maybe the first flyby, the kind of very qualitative, maybe colloquium level take on what I'm going to describe, and then we're going to go through it in a bit more technical detail, since since this is a school, and I have to show you guys how things are really done. So why evolve? A question. Well, like I just argued, there is no energy or rapidity or x dependence in this classical field, and the results in cross sections, distribution functions, and everything. So what do? We have to find quantum corrections, which to this classical picture, which will bring energy and rapidity dependence, and those are included through the evolution equations. Let me stress from the outset that when in our small x discussion, we're talking about evolution equations, we're not talking about, say, DGLAP evolution, which is evolution in Q squared. We're not talking about CSS evolution, which is also an evolution in Q squared, but for TMDs. We'll be talking about evolution in a different variable in x. So the evolution will start at x naught and evolve, say, the PDFs or TMDs down to small x, and will predict the x dependence of these observables, rather than, say, DGLAP evolution predicts Q squared dependence of distribution functions. X evolution will predict x dependence of observables. So it's a different type of evolution. The earliest example of evolution in X is a so-called BFKL equation due to Bolitsky, Fadin, Kuraev, and Lipatov. Here you see all their pictures. And this is, like I said, very sort of qualitative representation of BFKL shown here diagrammatically as follows. Suppose you have a proton which has lots of quarks and gluons, but say we only look at gluons, which are just those straight lines. And as we increase the energy, as we boost the proton down the beamline, right, we increase the phase space, and we have a possibility of emitting an extra gluon, right? If we have more energy, we have more phase space, why not populate it by emitting one more gluon? Again, the gluons are straight lines just for simplicity. If you start drawing wiggly lines, it gets a little messy. Okay, so splittings may happen, and the new gluon may be emitted off of any of the pre-existing gluons. So we can think about it and say that the number, if n, we know n, of course, ultimately will be the dipole amplitude, but let's talk about n as a number of gluons. If n was a number of gluons, as we decrease Bjorken x or increase energy, the increase in n should be proportional to n, right? This is what happens when your new gluon is emitted off of any of the n pre-existing gluons. Of course, proportional is a very strong statement. You actually do the calculation. There is an integral kernel here with a convolution over transverse momenta. This is all there, but the physics message is very simple, right? The increase of the number of gluons is proportional to the number of gluons we had before that step. Okay, so this is the essence of BFKL equations. And for now, forget about the fact that K is an integral kernel. Think of it as just some proportionality constant. So what happens is you start with a proton at some x naught. And remember, I told you I want to evolve down to smaller values of x smaller than x naught. And as I go to smaller values of x, BFKL equation keeps producing more and more gluons, right, in a very linear fashion. And you have lots of gluons. They roughly all have the same transverse momentum, which means that if I want to draw the proton in a transverse plane, so the proton is coming out of the screen towards us, all those gluons roughly have the same transverse size. So if we produce a lot of them, all roughly the same transverse size, they just end up kind of sitting on top of each other and overlapping, and they'll start producing high density regions inside the proton. Okay, so fine, you say great, but that is not a major crime. It's producing some dense regions, very well, so be it. The number, you can also argue that the number will grow exponentially. Remember, we have a linear equation. The solution of a linear equation is usually an exponential in log 1 over x. So if we write the solution of BFKL equation, and that's actually true with some caveats for the solution of the full BFKL equation, but the solution of a toy BFKL equation, delta is what we used to call the kernel, or alpha s times the kernel. So think of it as some number here. The solution is just an exponential, but exponential of a log is just the power of 1 over x. So the solution of a BFKL equation is just this power of 1 over x, so power of energy grows of the cross sections, or power of 1 over x grows of the PDFs, and power of energy grows of the corresponding scattering cross section, right? Because if I scatter something on this proton, now it has a lot more gluons than when we started at larger x, at lower energies. The cross section will grow correspondingly. But the question is, okay, fine. So we're creating these dense regions, but can these dense regions get infinitely dense? Can the corresponding gluon fields be infinitely strong? Can the cross sections corresponding to the scattering rise forever? Right? If the cross section in the previous slide we had a number of gluons which would lead to the cross section which grows as a power of energy, can that be true? No, we still have the same black disk limit, right? 2 pi r squared that we discussed last time. So the cross section that grows as a power of energy would sooner or later violate the black disk limit. So something has to happen to stop this growth of density, of the gluon density. What happens is, again, easier to explain in terms of this Stickman view of the proton. So again, the straight lines are all gluons, and we discussed how BFKL was driven by the splittings. But imagine you have a proton and you had many, many splittings. Again, you populate the whole proton with a lot of gluons to the point that the gluons got nowhere to go. The analogy I usually mention here is in biology. You have many of the same processes, but suppose you have a bacteria living in a petri dish. So you put a petri dish, you put a culture of bacteria in there. The bacteria start, if the conditions are right and the bacteria are happy, they start multiplying, they populate the whole petri dish, but then they got nowhere to go, right? They kind of exhausted all their space they were given. What happens then? Well, after a while, they start turning on each other, right? And they start eating each other up because they can't just multiply anymore. There's at some point virtually no space. By the way, I'm not a biology expert, so this is a very bird's eye view of biology. And if there are better experts in the room than me, hold your criticism of biology analogy. But I think you're getting the idea that when the system gets very dense, gluons can recombine. Recombination becomes as important as splitting eventually. And indeed, you can do a simple calculation. Remember, splittings was proportional to the number of gluons existing in the proton. Recombination requires 2 gluons to come together. So recombination should be proportional to the number of pairs, roughly n squared over 2, but we're not counting factors of 2. And so the evolution equation, because of this recombination term, gets modified. The BFKL evolution equation gets modified by this quadratic term proportional to n squared with some coefficient, with some kernel as well. But in some approximation, it can be even written without the kernel acting on it. The point is, one gets a nonlinear evolution equation like this. And then you see that when n gets sufficiently large, when the number of gluons gets sufficiently large, instead of just growing like they did for BFKL evolution, the quadratic term would sooner or later catch up, and it would compensate for the growth from the linear term. So when the gluon density gets very large, the splitting and recombination effects balance each other out, and this is the phenomenon of gluon saturation in terms of small x evolution equations. Okay, so this is the idea of saturation, that this evolution in x at very small x, when the systems get very dense, the evolution equation in X is not a linear BFKL equation, but a nonlinear evolution equation, including this additional quadratic term. What it does, of course, is it modifies. So this is again a sketch by hand. Don't hold me accountable for anything other than qualitative features of this plot. This is, say, the DIS cross section as a function of energy. BFKL, for instance, would just give us power of energy growth, as we discussed briefly a little while ago. But then saturation effects would come in and reduce this power of energy growth. And actually, you have to do a calculation to show that it's going to be log cube of energy. What's important is that we don't have any more power law of energy growth of the cross section. And this is how evolution will get us into the saturation regime. So this is sort of a bird's eye view of the big picture. And now we can start a more in-depth discussion in terms of Feynman diagrams and connecting to what we discussed last time. But before we go there, is there any questions?
Any questions?
Just one. Yep. So you talk about this basically, the more you have, the more you get as you go up at speed. It's exponential. So at some point you say it fills up like biological model. There's no more room. Is this is there some natural limiting that you have in the model, or is it something you put in posteriori, or how does that work?
Well, the way it will work, you'll see in a little bit. You actually do the calculation, and you you realize that, well, okay, very loosely speaking, at this level, you realize that diagrams, the recombination diagrams, which are initially very small. So imagine that n is sort of proportional to the number of gluons, but it's not really the number of gluons. It's really a normal. It's a quantity more like the dipole amplitude, which is never above 1, right? So imagine that you start with n being very small. If n is small, n squared is a term you can forget about, right? So you start with n being small, and you start running the evolution, which will be BFKL evolution. But n, as a result of this evolution, n will grow. And then when n gets larger and larger, eventually this quadratic term becomes more important. And that's not a model. It's just a result of calculating these recombination diagrams, which are always there, but initially they were not important, and then they will become important and bring in the saturation effects. So and we'll see in a bit more detail in a few minutes what I mean by that in the language of the previous or yesterday's discussion, but it's really just a diagrammatic calculation.
Thank you.
Yeah. Okay. Sure.
Thanks, Yuri.
Okay, if there are no other questions, let me try to move on. So let's go back to the discussion we had yesterday, and I just refreshed your memory a little bit about it. All right, in the classical picture, we just had, remember I told you all the QCD physics is in the dipole or for DIS cross section was in the dipole scattering on the target, say target nucleus. Question is, well, is that all there is to it, right? Why is there just a dipole that scatters on the nucleus? Why can't the quark and antiquark emit a gluon here? Kind of somewhat a jagged line, but why can't they emit a gluon that would also interact with the nucleus, like a long-lived S-channel gluon? Well, you say an extra gluon is an extra suppression by power of alpha S, but if you integrate over the phase space of this gluon, right? The gluon has some transverse momentum, the gluon has some longitudinal momentum. You integrate over those momenta. It turns out that the longitudinal momentum integral gives you a log of energy, a log of 1 over x, or equivalent factor of rapidity. So yes, indeed, extra gluon emissions are suppressed by powers of alpha s, but they're enhanced by logs of energy. So it may, if the energy is large enough, or x is small enough, it makes sense. It may make sense to resum all such corrections, alpha times log of energy. So you don't stop at just one gluon emission, right? You can emit 2 gluons, 3 gluons, etc. You can actually picture a cascade of gluons that would be developed inside by this dipole. And then this whole slew of gluons would interact with the target nucleus down here. So this is what we want to do. And this would give us a resummation of powers of alpha s log energy or alpha s log 1 over x. So you can imagine that, again, our power counting is such that alpha log energy is order 1. This is known as a leading logarithmic approximation, or LLA. And higher order corrections, say alpha s squared times log of energy, we're going to leave off for now. Of course, they have been calculated, but that's our discussion here sort of concentrates more on the leading order calculation than NLO calculations. Of course, NLO corrections are very important, and that's a whole separate story. Okay, how do we? So we want to kind of one other thing I wanted to mention, that you don't have those emissions when the dipole goes through the nucleus, because everything I drew here is not really drawn to scale. Remember, I told you that the dipole is produced by the virtual photon way before scattering on the nucleus. So there is a time scale separation that it takes the dipole a long time to develop all those gluons. And then the system scatters in the target nucleus of proton, and then all those gluons recombine back into the dipole again if we're interested in the forward scattering amplitude. And the interaction with the nucleus happens very fast. So it's not drawn like this here, but all those multiple rescatterings, all those gluons, those are Glauber gluons, right? Those are instantaneous gluons. And they happen very, very fast, say along the x minus direction. So really, it takes a long time to develop this cascade, and the interaction happens so fast that during the interaction, we have no time to emit additional S-channel gluons. So all the gluons are emitted and absorbed either before or after the interaction with the target. The gluons are not emitted during the interaction with the target. And that's the essential separation of scales. Technically, if you emit a gluon during the interaction with the target, that is suppressed by a power of x, of Bjorken x. And we're looking at in the regime of small x, so that's a very, very strong suppression. Okay, how do you sum up a cascade of gluons, just an avalanche of gluons? Well, it's not easy to do exactly. So one trick to do, one trick which allows us to resum this cascade is goes by the name of Mueller's dipole model, invented by L. Mueller back in the early 90s. And it says that you have to take a large NC limit. So NC is a number of colors. You can take a theoretical limit where NC is large, then corrections to it will be suppressed by 1 over NC, or actually in case of gluons by 1 over NC squared. If you're worried that 1 over NC is just 1/3 and it's not really a small parameter, well, Ed Witten back in the 80s, I think, came up with the argument that in QED, in electrodynamics, E, the electron charge in natural units, is about 1/3 as well. And the perturbation theory in electrodynamics works very, very well. Anyway, we'll touch upon how good the large NC approximation is again later, but here is the idea. So let me just get the feeling, how many of the students in the room know the large NC approximation?
Large NC.
Please raise your hands. I'm trying to see. It's a very small.
More than 3 students know. So it's a large number.
Out of a couple of dozen or so. Okay, very good. So great. So it's good that I have a little bit of an explanation on this slide. So large NC limit was invented by Tooth back in the 70s as a theoretical tool, as I already mentioned. And so here is, so at the bottom of the slide is really the explanation of a large NC limit, right? So if you studied the representations of Lie groups at any level, and I think it's probably safe to assume that most of the students in the room have studied this. So if you take a 3 cross for SU3, if you take 3 cross 3 bar, this is 1 plus 8, right? So the fundamental representation and the conjugate fundamental representation, their product is a singlet plus an octet. Is that familiar to most people? Yes, I see some notes. Okay. If it's not familiar and you want me to explain it, I sort of could, but maybe we can. Yeah, so if somebody really wants it to be explained, I could. Okay, sounds like everybody is comfortable with it. I'm sorry, I don't see you guys very well, so it's hard for me to judge the reactions. But suppose your group is not SU3, but SUNC, right? Make a number of colors a variable. Actually, the same relation still holds. Well, a similar relation still holds. It's NC cross NC bar. Again, the fundamental and the conjugate fundamental representations. You take that product. It's a singlet 1 plus NC squared minus 1. And NC squared minus 1 is known as the adjoint representation, right? 8 is the adjoint representation in SU3, and C squared minus 1 is the adjoint. Sorry, don't know what I did. Is the adjoint representation is in SUM. Now, if NC is very large, the dimensionality of this representation is much larger, right? So you always much larger to be in adjoint representation. So in other words, if you take a quark anti-quark pair, and C is very large, the odds of that quark anti-quark pair being in a singlet is very slim. Most likely, the quark and anti-quark are in an octet, in a joint representation. So we can say that at large NC cross NC bar is approximately NC squared minus 1, and vice versa. If we take a gluon, which is in a joint representation, by definition, it is in NC squared minus 1, we can write this as NC cross NC bar. So in other words, we can replace a gluon by a quark anti-quark pair. And the pair is not in the color singlet, it's color adjoint pair. Or it could be color singlet, but that's a minor correction, which we're willing to absorb because it's suppressed by NC squared, right? So what I'm trying to say is, suppose we take a dipole and we emit a gluon, this will be a line here. At large NC, like I just mentioned, we replace a gluon by a quark anti-quark pair. So we replace the gluon line by a double line. This double line, I kind of tried drawing quark colors here, right? So if the original dipole was, say, red anti-red, the quarks in the dipole were red anti-red, we emit a gluon. Sorry. Something is very sensitive here. I'm not sure what. Okay, so we emit the gluon. It's a quark anti-quark pair which have different colors. So we can say that this is red and anti-blue quark lines, and then the original red quark line becomes a blue quark line, right? When you emit a gluon, the color of the quark is almost never the same. So this would be blue anti-blue, and our original dipole. So it's kind of still there. We still have a red anti-red dipole, but it's different size, right? The original dipole was made by, say, quark and anti-quark lines. Now it's the quark part of the gluon line and the original anti-quark which form a dipole, red anti-red, and the original, what was the original quark line, which is now blue colored, with the anti-quark line of the gluon forms another dipole. So in other words, a gluon emission here splits the original dipole into two dipoles, blue anti-blue here and red anti-red. Of course, in the end, we sum overall colors in each dipole, but what's important is we have two separate dipoles. If we have more emissions, if we emit another gluon, we split existing dipoles into two again, right? So instead of, if we emit a gluon down here, for instance, this red anti-red dipole would be split again, and we will generate a new green anti-green dipole, and we have the original red anti-red and the blue anti-blue we have created in the previous step. So after two gluon emissions, we may have two dipoles. Of course, there are virtual corrections as well. The emissions don't always have to produce a gluon here, right? The gluon can be reabsorbed, but that doesn't break the whole picture that at large NC, the cascade of gluons can be thought of instead as a cascade of dipoles. And you say, okay, well, what's the big deal? Well, the big deal is that dipoles are kind of self-replicating. As you can see, dipoles produce more dipoles, and then we can write a closed evolution equation in terms of the this dipole amplitude, and which we talked about last time. Any questions about this picture? All right, looks like it's all crystal clear. If it is, let's move on.
Can I ask a question? So
Did somebody say? Yeah, okay, please go ahead.
you go back to that first, just one question about this. Earlier you're talking about these things that have been I'm sort of picturing a plane, but in real life, these dipoles, are these things all on some kind of plane, or what kind of, is there some kind of limit to how they appear? In other words, you start with a red and anti-red. So there you can always say, okay, they're on some plane as they travel, yeah? But when you split to the next one, we have the blue, anti-blue, red, they make the new dipole, are those things like, is there some limit to how the geometry goes in terms of the space they fill?
Yeah, that's a very good question. Let me switch to my iPad. By the way, some of you are responding to my questions in chat, I see. Unfortunately, when I'm sharing, I don't have I'm not always fast enough to see that. So I apologize if I'm not reacting to chat. And I think yesterday I didn't react to some comments in chat. I only saw them for a split second before the meeting was over, and I didn't have a chance to read them. So if I don't address someone's question, please feel free to email me later. Anyway, addressing the question at hand, what is the geometry, right? The idea is, the rule is as follows. At large NC, and that was Tooth's main insight, we have only planar diagrams contribute. What does it mean? Suppose I have, let's put it this way. Suppose I have a dipole, right? And I'm going to draw it this way soon, but okay, this is, so somewhere here we have all the interactions with the target, but let's forget about them for a moment. So suppose I emit a gluon like I've been showing to you guys, and then the gluon gets absorbed down here, right? At large NC, we draw it as a double line like this. And by the way, because it's a dipole, it's understood that the color kind of connects this way, right? Say this is a quark line, this would be the anti-quark line, so the color kind of flows back around here and here. Okay, so now at the time of the interaction with a dipole, we have, with a target, we have two dipoles, and that was maybe not on that slide. That was the blue anti-blue and red anti-red. Now, question is, and I said that the dipoles self-replicate, and that was maybe a little too fast. The answer is the diagrams which survive the large NC limit are the planar diagrams. At this level of one gluon emission, it's a little hard to see. It would be doable if I include more detailed interactions with the target, but let's not go there yet. Suppose I want to emit two gluons. I emit one gluon, and say I want to emit the second gluon, but I want to emit it like this. So it kind of jumps over the first gluon, and this is this diagram. And again, the color all loops back together. It's all kind of short-circuited there. This diagram is not a planar diagram, right? Because clearly one gluon kind of hops over another. So this is an example of a non-planar diagram. The conclusion is, as you can actually see it by direct calculations, or you can see it diagrammatically, it is NC suppressed. Well, let's see it first by direct calculation. That's probably the easiest thing. So imagine that the interaction with the target, it happens here, but say it's all color singlet, doesn't change the colors at all. It's a very, very simple, simplistic model of the interaction with the target, but let's leave it like this. Suppose this gluon has color A, this gluon has color B. We have some direction here, right? We just go around the loop. This diagram gives us trace of, say, TB, TA, TB, TA. And I don't know what you guys know about the colors, but does anyone know what this trace is equal to? Okay, I'll take it as a no, but you do a calculation, you get CF over 2 with a minus sign. Right, you can just commute these two guys and either get a trace of 3 matrices which is tabulated, or you get after you commute them, you get TB, TB, TA, TA, and you use the fact that TA, TA is a Casimir, right, of the representation. Okay, are you guys on the same page? I really can't see. So what I'm trying to say is we have to compare it. Okay, so how is it suppressed? NC, by the way, right, is sorry, CF is NC squared minus 1 over 2 NC. It's a fundamental Casimir of SUN. What do you compare it with? Compare it to a planar diagram. So let me draw an example of a planar diagram where the gluons don't hop over each other. For instance, you have a gluon like this and a gluon like that. All right, no jumping around. It all kind of fits in one plane. This gluon has color A, this gluon has color B. We calculate the trace. Again, trace is going to be, say, T BTB, TA. And like I just said a minute ago, TB is just CF times a unit matrix. TA is also just a Casimir times a unit matrix. So we get CF squared NC. Right, trace of a unit matrix, fundamental trace of a unit matrix is NC. So this is NC squared minus 1 over 2 NC squared times NC. Or if NC is very large, we see that this is NC cubed over 4. And the previous diagram for large NC was minus NC over 4. So you see the non-planar diagram was order NC. The planar diagram is of order NC cubed. Clearly it dominates. Okay. The other way to do it is there is sort of a rule of thumb, not quite accurate, but accurate in most cases, that each loop in this large NC picture, when we replace each gluon by a double line, each loop brings in a factor of NC over 2. And by loop, I mean you just, jump on one of the quark lines and travel all around where you can go as long as you come back, right? So for instance, here I can just loop around this line. That gives me an NC over 2. I can loop around that line. This gives me another NC over 2. So similar analysis could be done for these diagrams up here. For instance, we can start with a planar diagram and draw it in a large NC limit, like this. Sorry, a little untidy. Let me fix it. Just like that, right? That's a large NC representation of this planar diagram. And then you see you have a loop going here, right? We can travel around the quark loop. There is another loop. Okay, very skinny in my drawing down here. And then there is a big loop in the middle. So by that rule, this thing should be NC over 2 cubed because there are 3 3 loops. Okay, we're off by a factor of 2 compared to the exact calculation, but at least we got the power of NC, right? Whereas this non-planar diagram, if we redraw it again with a double line, that's a little harder, right? We have, so let's start by drawing the first gluon. No, sorry, I'm not doing it right. Okay, so we have something like this, and then we'll have something like that. The first gluon was going down like this. The second gluon went up like that, and they hopped over each other, right? It's not a planar diagram, so we have to introduce some sort of a jumping over. So you look at this, and so you hop on one of the quark lines, and you start moving around the diagram, and lo and behold, after a while, you realize that you actually looped around the whole thing, and you're back to where you started. There's only one loop in this entire diagram. So naively, it's order NC/2. By that rule, I introduced to you guys that each loop is NC/2. Well, again, we're off by a factor of 2 and a minus sign, but you know, who's counting 2s and minus signs between friends? Bottom line is, again, we see that this is a subleading NC diagram. It's non-planar. We also see that this non-planar diagram doesn't have colored dipoles, right? So if there is a time of, if this is the time when we interact with the target, by the time we interact with the target, we have 1, 2, 3, 4, 5, 6 quark lines, or quark and anti-quark lines, effective quark and anti-quark lines. All of them are the same color, right? So this is not a colored dipole. This is color sextuple, right? I'm not sure I'm spelling it right, but okay. The point is that not everything is colored dipoles, but at large NC, dipoles dominate, and higher order objects like quadrupoles, I guess sextupole, right? All those high order correlators are NC suppressed. So sorry for such a lengthy answer, but I thought that's an important point to make, that large NC means planar diagrams contribute, and that does eliminate quite a number of non-planar diagrams which are NC suppressed. Did I answer the question?
Mostly. Just one last tiny detail. So topologically, they need to be on this sort of flat surface, cut like a puzzle, the way you do this. But just one last thing is that if I'm physically making a dipole in space, I can still deform that plane then, as long as I keep it sort of topologically the same, or is it literally a plane in physical space?
I'm not sure I'm quite catching the question. So you're saying you can deform a dipole into what?
Well, I'm saying that, so in the earlier lecture you have these two dipole, this dipole that are literally stuck in time, right? They're not changing distance from each other. Now we bring more dipoles. But as we do that, if I'm physically looking at this head on, if I'm looking at this sort of like a circle, and I have these dots coming at me, when these dipoles form, I understand that they have to be topologically like a puzzle to be not suppressed. But I wonder, can these other dipoles be, can they be at sort of angles with each other, or are they literally stack in a line?
Okay, right. Good. Sorry, I didn't maybe catch the question. But now I understand. So indeed, all I'm drawing here is topology. So this is topology. The way it actually looks like, right? You start with so if the dipole is coming at us out of the screen now, we have quark and anti-quark, right? We emit a gluon, which becomes a quark-anti-quark pair. The gluon can be anywhere in the transverse plane, right? So this is a transverse plane. A gluon can be emitted anywhere. So we can split our original dipole into two dipoles. I'm kind of drawing them as those elongated things. So this is a dipole. Of course, you have some anti-quark line of the gluon, and here you have a quark line of the gluon and an anti-quark, and this is another dipole. So that's one step of evolution. At the next step, you can create three dipoles by emitting two gluons, right? So you emit one gluon, and I don't know, to make it really complicated, we can emit another one here. So you may you might have had the original dipole that was just Q bar here. Here you have Q and Q bar. You may have this thing, a dipole, that thing, a dipole, and this thing, a dipole. So you have three dipoles. In transverse plane, they are, you'll see in a minute, there is an integral kernel which gives some distribution of probabilities where they can be emitted in the transverse plane, but in principle, they can be emitted anywhere. So this is some Q bar and Q, and this is, I don't know, Q bar prime, Q prime, right? And we have now three dipoles. Does that address the question, or am I on the tangent again? Yeah, it's good.
Thank you.
Okay, all right. Is there any other questions in the room? Okay, seems like no. So let's go back to the PowerPoint. Oh no, time flies. Okay. What in a large NC limit, instead of a cascade of gluons, we have a cascade of dipoles. So this is a very schematic representation that a virtual photon in DIS came in, split into a quark and anti-quark. They produced a cascade of gluons, which in the large NC limit, we replace those gluons by double lines, and we have those dipoles formed by between those double lines. And this kind of dangling lines means that the gluon can be emitted in many different ways. I'll maybe go through it in a bit more detail later. And then when this cascade comes and interacts with the target, each dipole interacts with the target independently. Again, it's a property of the large NC limit. And also, I guess for this large nucleus target, it's a property of a large nucleus where it's always advantageous to interact with different nucleons rather than multiple interactions with the same. And then, again, for the forward amplitude, we recombine all this cascade of dipoles back together. So the notation at large NC is the follows, like I just showed you, this dangling kind of disconnected. So this is what I was drawing on iPad. So dashed line is a very fast, very instantaneous interaction with the target. This is a dipole that comes in and produces a double line, which is a gluon. Now the gluon can be emitted, say, by the quark or by the anti-quark line to the left of the interaction with the target, and also can be absorbed by either the quark or anti-quark lines to the right of the interaction with the target. So you have four different situations here, and instead of drawing all four of them, it's easier to draw a single diagram like this with a gluon line kind of disconnected, but that means we can connect it to the top or to the bottom. One can also have virtual corrections, also shown by disconnected diagram. Examples of virtual corrections are here, right? You can emit a gluon and absorb it still before the interaction with the target. And you can have emission and absorption happening on different lines, on the quark line and anti-quark lines, or they may happen on the same line, obviously, like a self-energy correction. So you have, all that notation, and now we can write down an evolution equation for something called the S matrix. The S matrix is 1 minus the scattering amplitude. So loosely speaking, remember S matrix is 1 plus IT, where T is the T matrix. The dipole amplitude N is really the imaginary part of the T matrix, and therefore, and that's the one that dominates in high energy scattering. So the S matrix can be written as 1 minus N. Anyway, the evolution equation one writes is as follows. If you start with a dipole, you increase rapidity, or you decrease x, or you increase energy, it's all the same. Per one step of evolution, you emit a gluon, and the dashed line is the interaction with the target, and this shaded blob here means everything, right? We have this cascade of gluons / dipoles we have to resum, and then that cascade interacts with the target at this dashed line. So in one step of evolution, we can emit a gluon, which splits the original dipole, say 1, 0. We'll label the lines here. Quark line is 1, anti-quark is 0. So we have a quark anti-quark 1, 0 dipole. We emit a gluon 2, which splits the original 1, 0 dipole into 1, 2, and 2, 0. And that's the real emission corrections. And then each of these new dipoles, dipole 1, 2, and dipole 2, 0, they can separately, independently interact with the dipole through their corresponding, interact with the target. I'm sorry, I don't know why I'm making the same mistake. Interact with the target in an independent way through their own S matrices. Or you may have virtual correction here, which would leave the original dipole 1, 0 intact, and then the original dipole would again interact with the target, or develop the subsequent cascade and interact with the target by itself, or the products of that cascade will interact with the target. And similarly, you can have virtual correction to the right of the target. So virtual corrections usually come with a minus sign. So we get an evolution equation for the S matrix that dy is a derivative with respect to rapidity. S matrix is S. We get an integral kernel here of x01, x02, x21 are the transverse sizes of all these dipoles. X10 is our original dipole size, x21 and x20 are the daughter, it's called daughter dipole sizes, the dipoles produced by this one step of evolution. So the first term, the splitting, the one that splits the dipole in two, comes in with two S matrices, and then virtual corrections in the second line of the diagrammatic representation come in with a minus sign. So we have this nonlinear equation for the S matrix. And if we want to write it for, rewrite it for the dipole amplitude n, like I argued, n is 1 minus s. So for n, diagrammatically, it looks like this. You have a couple, we have several linear terms, and then you have a quadratic term. So really, it's just a simple replacement of s by 1 minus n. Bottom line, you get this nonlinear evolution equation. And n now is the dipole amplitude, the same dipole amplitude we talked about much of our previous yesterday's discussion. So we have this evolution equation. It has 4 terms on the right. 3 are linear in n, and 1 is quadratic. The linear terms constitute actually the same BFKL equation I briefly mentioned already. So if the amplitude is very small, if the dipole amplitude n is very small, we can drop the quadratic term n squared and keep only the linear BFKL equation, and that would give us something that grows with energy unchecked. But the quadratic term would eventually come in as n increases and introduce the effects of saturation. You may ask me, well, in your previous kind of discussion, this saturation effects came in through mergers. Where are the mergers? And my answer is, one man's mergers are another man's splittings. So what we resummed were splittings, but we were running the evolution from the dipole, from the projectile prodding the target, proton or a nucleus. One can also run the same evolution the other way from the target, and then all those nonlinear effects would come in as mergers. But that's much harder to do. So we do the easier thing, and that's running the evolution from the probe, from the dipole. Okay, any questions so far? All right, sounds like. Did somebody say something? No?
Any questions?
Sorry, I didn't catch that.
There are no questions right now.
No questions. Okay, very good. Or not, but nonetheless, we can ask them later. Okay, so this is the same equation written in a slightly different way. It's a differential equation. Rapidity to solve it, you need some initial condition, and as the initial condition, we can use this quasi-classical multiple rescattering Wilber-Mueller formula, or equivalently Maclaurin-Nagopulan model, which gives us this dipole amplitude as this 1 minus exponential that we talked about last time. So this dipole amplitude, remember I said earlier, it had no energy dependence, no x dependence in it. So we can kind of set it as the initial condition at some y equals y naught. And then we have a first order differential equation to solve. If we specify the initial condition, the solution is unique. And once we solve this equation, we get the energy dependence of the dipole amplitude, and therefore the x dependence of the structure functions and PDFs. Okay, quick word about resummation. So in the large and C limit, so the small x evolution resums powers of alpha times y, or log of energy, or log 1 over x. Large and C, in the large and C limit, we also have a factor of NC. So we're resumming powers of alpha and C and y. And the initial conditions resum, if we have a nuclear target, they resum powers of alpha squared a to the 1/3. Now, one can go beyond the large and C limit and talk about a JIMWLK evolution equation. And I think in the interest of time, I'm just going to flash a slide or two saying that it exists. So it's harder to go beyond the large and C limit, right? Like I showed you in an example on an iPad, you don't have dipoles anymore. You have quadrupoles, you have sextupoles, you have all sorts of color structure. You have double traces of Wilson lines. Things get very, very complicated. So the point is the equations don't close, right? At large and C, you have a dipole amplitude on the left and a dipole amplitude on the right. So the equation is closed. Beyond large and C, the equation doesn't close. So it's not something you can easily solve even numerically. So instead, people use a different approach based on a kind of functional differential equation called the JIMWLK evolution equation. And the JIMWLK evolution equation says that if we have, well, it's a sort of a very different philosophy, though ultimately physics is very similar to what I was just describing. If we have some operator which we want to find an expectation value for, we kind of take this operator and average it over all, say the operator depends on A plus, the Eikonal strong gluon field of the proton. We have to average it over all A plus with some weight functional W. And the operator could be, say, a pair of Wilson lines, could be a trace of 2 Wilson lines, which is a colored dipole, etc. So this functional, this weight functional W is, of course, an unknown object, and one can write down an evolution for it, which is this JIMWLK evolution equation. So it's a functional, it depends on alpha, which is a function, which is a field of the target, and its evolution in rapidity is given by this JIMWLK evolution equation. So the idea is, if you want to go beyond large and C limit, you have to solve this equation. Only numerical solution is possible. You solve these functional equations, and then if you want to calculate an expectation value of some operator, you just convolute it with the weight function you found from solving that evolution equation, and integrate over all. So integrate it over all fields alpha, which is sort of a shorthand for A plus Eikonal gluon field. Bottom line is, say, if one is interested in the dipole amplitude, though, it seems like the one can take the large and C limit, solve the evolution equation I just showed you. Well, I showed you earlier, and then compare it to the JIMWLK result for this dipole amplitude. And interestingly enough, the correction turns out to be corrections, at least for realistic energies, for anything most of us will see in our lifetime, maybe all of us will see in our lifetimes, the correction is about 0.1%, 0.001, the relative difference between all NC and large NC limits here. So naively for gluon dynamics, like I was describing, large NC limit is accurate up to maybe 10%, but somehow there are certain things at work which you don't completely understand, but the large NC limit here works up to, down to 0.1% correction. Of course, if you go down to higher and higher energies, extremely high energies, eventually it will be larger than 0.001, but like I said, that's not likely anytime soon. Okay, so of course there are other, and I don't have the time to discuss it, but there are other observables like quadrupoles and double trace operators, etc. Which some of them, some linear combinations of those operators are subleading NC at the leading order already. They're just subleading NC, and then one needs to use JIMWLK evolution to study them. Anyway, bottom line is, if this was a little confusing, there is a JIMWLK equation which is functional and complicated, but this is the one that tells us how to evolve in X beyond the large NC. Okay, let's move on. If there are no questions, let's move on to solving the evolution equations. And I'm going to go back to the large NC limit and solve the equation for the dipole amplitude. And the solution, the exact analytic solution, which is valid in all regions, is not known. There are various approximations in various corners of phase space, which I'm not going to, I don't have the time to discuss. So here is a numerical solution. And so this is the dipole amplitude again, m, as a function of x perp. This is not a sketch I did by hand, but actually a plot done by people much more numerically astute than me. So again, you see that when x perp goes to 0, the amplitude goes to 0. When x perp goes larger, there is a black disk limit at 1. And the initial condition, this Glauber-Mueller multiple scattering formula we talked about, is this dashed line, black dashed line on the far right. And what we see is, as so we set our initial condition by putting rapidity to 0 effectively there. Rapidity is never exactly 0, but if it's not large enough, we put it to be equal to 0, sort of as a starting point. You can always redefine the rapidity shifted by a constant. And then you increase the rapidity or increase your energy in steps. And what happens is the initial condition evolves into the first this line to its immediate left, then further to the left, then further to the left, and further to the left. So as energy increases, the transition from this kind of linear or power law in x perp growth regime to this black disk limit, the saturation transition, keeps moving further and further to the left. And remember, the transition is given by 1 over QS, 1 of the saturation scale. So you see that 1 over QS decreases with energy, all right? The transition is going from right to left. So 1 over QS, as I increase energy, it decreases. So that means QS increases with energy, okay? And also the evolution preserves the black disk limit, unlike BFKL, which would have just taken that dashed line and would have made it go up everywhere. The nonlinear evolution equation preserves the black disk limit so that n is never above 1, the dipole amplitude. Okay, but what I showed here is that it seems like saturation scale increases with energy, and that's indeed the case here. One can extract the saturation scale from the same numerical solution and plot it as a function of energy. This is a log plot on the vertical axis and a linear plot on the horizontal axis. You can see that log of QS goes linear with rapidity like this. At higher energies, initially maybe it's not quite linear, but eventually it becomes linear. So we see in another important regime feature. So first of all, the nonlinear evolution does introduce energy dependence of this amplitude, which we didn't have in the quasi-classical picture we discussed last time. Second of all, the result is that the saturation scale keeps growing with energy and rapidity, as I promised in the very beginning. Another sort of a neat feature is that the infrared sensitivity. Remember, I kept arguing the saturation scale is something that saves us from venturing too much into non-perturbative low momentum physics. And this is shown here. So this is sort of it's a momentum space plot. So you can think of it as, so the vertical axis is log1/x or rapidity. This people down here, they started their evolution really at x equals to 1, just for the purpose of sort of understanding its feature, not in terms of being realistic or anything. And so they evolve up here, and they initiate everything with some sort of a simple delta function momentum space at 1 GeV. So it's like, imagine you have a, I don't know, a TMD where all the gluons are sitting at 1 GeV in KT. Not realistic, but sort of it's sort of the initial condition just to initiate the evolution and see what happens. And what happens, there is a problem with BFKL I didn't mention. You see the contour plot for BFKL solution is by those thin dotted lines. See what happens, you kind of initiate your evolution here, and then BFKL spreads into UV to high momentum and to the infrared. So the BFKL solution actually hits the infrared, right? If you have some non-perturbative physics happening on the left here, BFKL's equation just drives straight into it. And then, of course, it stops being valid there because the coupling gets large. Whereas in nonlinear evolution, because we have saturation effects which are screening the infrared, they are suppressing the infrared contribution. So this nonlinear evolution is different, and these are the solid lines here. You see the nonlinear evolution, the contour plot, everything just kind of goes to the right, and it really tends to avoid the infrared region. If anything, it moves further and further away from the infrared, which is good. It's sort of another consistency check of the approach. Okay, let me, I had a hyperlink and I forgot about it. So let me jump over it because I don't have the time. Let me kind of summarize this discussion, and then in the remaining 0 minutes, we'll talk about TMDs at small x. So what we talked about is how, as we go towards lower x, we get this new dense system of gluons with splittings and mergers happening at the same time. People also call this, so I've been calling it a saturation regime. People also call it colored glass condensate. So that's one of the standard terms. Physically, again, I gave you the statement that saturation scale grows with energy as a result of a numerical solution of solving this nonlinear evolution equation. But we can kind of understand it physically in this plot where we plot log q squared and log on one axis and log 1/x on another one. So high energy is up here. The size of gluons, right, 1 over the resolution scale increases to the left, decreases to the right. So you can see that, say, if you start with some system of gluons, and I had similar plots before, not quite exactly the same, as you go down in x, you produce more and more gluons until you get a very dense system, right? If you are at higher q squared, where your gluons are smaller, it would take you longer in terms of rapidity of log 1/x to get to a dense system of gluons. So you kind of can see that there is a line, there is a border here of the dense system, and dense systems are harder to reach if you are at larger q squared, just because your gluons are kind of smaller there. Of course, in the de Broglie wavelengths sense, so there's through-point particles. So your saturation regime is up here at small x and at not very large q squared, and then the border goes like this, which does mean that so this border, the saturation scale, is increasing with log 1/x, and this is what we saw numerically. This is sort of a more somewhat more scientific picture of the same thing. This is what we put in the EIC white paper. This is log q squared, log 1/x axis. The non-perturbative region is down here. It's still with us. But the hope is that saturation region kind of extends far enough outside of this non-perturbative region to be perturbatively calculable. And the nonlinear evolution equations we talked about are the ones which get us in the saturation region. BFKL evolution is the one that gets us towards, evolves us in X towards the saturation region, but doesn't by itself handle that region. And evolution in Q squared, like DGLAP and CSS, are the evolutions which evolve us in Q squared to the right. So that's really the summary of this part of my talk. Okay, yeah. And you can convince yourselves that the straight line on this log-log plot means that QS grows as power of 1 over x, which is what I was advertising in the very beginning of yesterday's talk. Okay, I think I can skip a few of slides which just reiterate the point. Somehow, quite okay. Let me just jump over it. Maybe this slide. So this is kind of a pocket formula in terms of saturation scale. It grows as a power of atomic number A. It grows as a power of 1 over x. The power of 1 over x is also roughly 1/3. So really this is what it is. And this, say, if you want to probe the small x physics, you can either go to very low x, which requires very high energy and a lot of money, or you can scatter on large nuclei, maybe on not such a small x, and that may cost somewhat less money. And that was one of the motivation for EIC, for the electron ion collector. Okay, there are some references if you guys want to read it, and of course the book Eugene Levin and myself wrote now already almost 10 years ago. Any questions?
Andrew?
Yeah, I had a question. Can you go back real quick to where you were just showing the plot of the different evolutions in Q squared or in?
Yeah. I know. I'm sorry. I have to jump over all this because somehow I'm in my office and I'm connected to a monitor. But is that the one you were asking about?
Yeah.
Okay.
So what if you suppose you started with something that was evolved in Q squared? So you start with something in DGLAP. Can you go up to the saturation region from DGLAP evolution, or do you have to start in that lower left corner there?
Yeah, I think so. The kind of the first approximation, the answer is no, because DGLAP evolves you up in Q squared, usually. So if you think of DGLAP as evolution towards higher Q squared, it clearly drives you away from the saturation regime, right? It drives you to the right. So by itself, DGLAP also is a linear evolution equation. It doesn't include saturation effects, right? It may drive you somewhere. So any linear evolution could drive you near saturation, but it wouldn't get you into the saturation regime because it doesn't include nonlinear saturation effects. So DGLAP doesn't have it. There is a double log, small x part of DGLAP where you resum logs 1 over x and logs of Q squared, which kind of evolve you towards the upper right regime. So yeah, I didn't have the time to discuss it, but there is this so-called GLR-Mueller-Chu equation. So Gribov, Levin, Riskin, Mueller-Chu equation. And Jean Wei, I think was one of the speakers in the school earlier. So that equation is kind of based on a double log DGLAP with a nonlinear correction added. So you can kind of modify DGLAP a little bit to have saturation effects in it. So it is doable, but it's sort of one can discuss because you kind of have an evolution in Q squared, and then you have a higher twist correction, like 1 over Q squared correction on the right-hand side. So it's not quite clear that this is quite kosher from the more formal standpoint. You're kind of mixing objects of different twists. But yeah, you can kind of modify DGLAP, double log DGLAP by hand and write GLR-Mueller-Chu equation, which would have saturation effects.
Okay, thank you.
Yeah, one last thing is people may ask, okay, why not run DGLAP towards lower Q squared? And people do it, my understanding, at of it is it's very unstable, right? So if you in principle you can set your initial conditions for DGLAP at large Q squared and run it backwards towards lower Q squared. Why not? But it's unstable numerically, and it may get you somewhere towards the regime at very small x towards near saturation. I have never looked at it, and I don't know. But the worry usually, if you ask, PDF experts which use DGLAB for global feeds and such, they don't like running it backwards. It's not very stable.
Okay, yeah, I think a better way of phrasing my question was, yeah, what you're saying right there. Would evolving backwards in Q squared and then up in energy be the same as evolving up in energy and then backwards in Q squared? But it sounds like you're saying that's just not stable. That's not practical.
It's not stable. I don't know if one, like I said, I don't know anyone trying to find saturation. Well, actually, maybe a long time ago there were efforts in the maybe Hegelian community looking for saturation. I think Nicholas Julassi was doing something like this. He wanted to evolve back in Q squared DGLAP and then compare it to GLR Muellers Chu. One probably could evolve backward. Like I said, you may come close to saturation, but DGLAP doesn't have saturation effects in it. So DGLAP is not going to give you saturation because it's a linear evolution equation, even if you're solving it backwards.
I see.
So, but it probably could get you close to the saturation region if the instability issues are resolved, and I don't know how. Okay.
Awesome. Thank you.
All right. We have 6 minutes, Chris.
About 10 minutes. We started late.
Excellent. So if there are no more questions, let me jump. So we already went to the conclusions. I just wanted to say that, okay, I wanted to mention it in more detail. Of course, it's, okay, this is a summary of what we just discussed. I'll just flash it and you can, it's all on Slack, you can read it. TMDs at small x, right? This is a TMD school. So the question is, can all this machinery I just described help us understand something about TMDs at small x? Can it help us understand the x dependence of TMDs? Again, usually when you solve CSS evolution for TMDs, you are establishing Q squared dependence. Yes, you do get some x dependence as well, but sort of as a byproduct of Q squared evolution. But can we write a dedicated small x evolution for TMDs? And yes, this is sort of a field which is developing now. But the answer is yes, we can use the small x machinery to predict a small x asymptotics of TMDs. I showed you the well-known table of leading twist Quark TMDs here. But in principle, maybe even higher twist TMDs are one can tackle using this technique. Since we have very little time, let me maybe just hit on some main points. So I kind of want to travel around this table. I don't think every TMD on this table we have. Yeah, I'm pretty sure not every TMD we know the small x asymptotics for in this table, but some of them, yes, we have studied. We being the small x community and TMD community. And let me just hit on some of the more important. Well, some of the results which have been achieved. So, for instance, one can start with the Gluon TMD, right? And I want to talk about unpolarized nucleon TMD. So imagine the proton is unpolarized, right? If the proton is unpolarized, that's the first row here. We have either just the unpolarized distribution or Bohr-Muellers. I believe Bohr-Muellers has not been studied at small x, but the unpolarized distribution has been studied. So this is an unpolarized Gluon TMD. I'll mention Quark one as well. I understand in the table we were looking at Quark TMDs. So this is a Gluon TMD. You have F plus I correlator. And for instance, you can, right, there are different Wilson line staples you can put. This is the dipole TMD. So I put a fundamental staple kind of going forward and another fundamental staple going backward. So this is the proton going along the light cone, the thick line, and the skinny lines are Wilson lines, and these I's denote the insertions of F plus I's at 2 different points, which are kind of maybe artificially stretched out to make them more, in the x minus direction, they stretched out to make them more visible. Right, so that's the arrows. So this is our TMD, and it's called the dipole TMD for a simple reason, because it really looks like a dipole scattering amplitude, right? We have a quark and antiquark scattering on the proton. And this intuition actually is quite right. Excuse me. This is indeed a dipole, so you can actually prove that, that this dipole TMD, F1G, is actually related to the dipole amplitude we just talked about. Namely, at small x, this dipole TMD can be written as just a Fourier transform of the dipole amplitude n. We spent all this time discussing in both of my talks. So if you're interested in x dependence of this TMD, you just need the x dependence of the dipole amplitude, which you Fourier transform into momentum space. Again, this is a small x notation. So in the TMD community, what I used to call x perp, somehow I'm calling it r perp here. This is what b perp is, and this b perp is really the input parameter of this dipole, which also needs to be integrated out. If I'm interested in small x asymptotics of unpolarized TMD, but say I'm not going all the way into the saturation region, I just want to know before I hit the saturation region, what is the prediction? Then I just solve BFKL evolution for the dipole amplitude, and I get a linear power of x behavior for this dipole Gluon TMD. This number comes to this 4 alpha and c over pi log 2. So this is an alpha s correction to the power 1. The 1 over x is just in the prefactor here. This correction is results from analytical solution of BFKL evolution. Unlike nonlinear evolution equations, we cannot solve analytically. BFKL evolution, one can solve analytically and obtain this power of order alpha s. And then if you solve NLO BFKL, you get the power order alpha squared, etc. Right? You have a whole perturbative series in the power here. But what's important is that the power is greater than 1, right? So this is the prediction for the small x asymptotics of this dipole TMDs. Well, Weizsäcker-Williams TMD, we talked about it yesterday when we talked about the Maclaurin-Venhoopelen model. So this is the Weizsäcker-Williams TMD. Again, we have f plus I insertions, right? But our Wilson line staple, you can think of it either as an adjoint Wilson future pointing, let's say SIDIS Wilson line staple, or you can think of it as 2 future pointing fundamental lines, right? Again, Gluon line is like 2 fundamental anti-fundamental lines, right? This is the distribution. It's a little harder to analyze at small x, but this is doable. I don't have the time to go to all the details. You can look in a paper by Dominguez and company. Okay, I mentioned here where they can be measured. That's not the point. It turns out that this Weizsäcker-Williams distribution is related to something called the color quadrupole. I mentioned sextupole earlier today, but you can also make a quadrupole out of 4 different light cone Wilson lines. Each V is an infinite light cone Wilson line at a different transverse position, x1, x2, x3, and x4. Bottom line is you have to write a separate evolution equation for the quadrupole. That actually had been done before, but in the linear regime, it still reduces to BFKL evolution. So this Weizsäcker-Williams Gluon TMD has the same small x asymptotics as the dipole one. In a linear regime, once you hit saturation regime, the 2 TMDs are different, but I'm not going there in this brief review. Similarly, and it's another whole separate discussion, one can look at the linearly polarized Gluon TMDs. So if you take f plus I, f plus j correlators, so now I and j are loose indices, then at the leading small x Eikonal regime, you can write this decomposition that the symmetric part of this correlator could be either delta ij or can be this structure, and this structure comes in with this H1 perp coefficient, the linear Gluon linearly polarized Gluon TMD. This has been studied by Andreas Metz and Zhang Zhao also by Adrian Dumitru, Vladis Kokov, and I think Andreas Metz as well. Bottom line, again, in the saturation regime, things are somewhat different, but outside the saturation regime, it's the same 1/x power. So given by BFKL evolution. Quark distributions, the same story at small x. Essentially, you can have all this gluon-driven evolution. The last minute, you can put a quark loop connected to the gluons, and that would be a quark distribution. So from that, you can argue that the quark, small x and polarized quark TMD should also scale in the same way as well at as the power of 1/x at small x as the gluon ones. So the mini summary here is all these unpolarized proton TMDs, not including Bohr Muellers, though, are scaling as 1/x to this power of 1 plus the BFKL correction. Okay, have probably 2 minutes. So let me say Sivers function. It's this TMD down here. It's a very famous one. I'm sure it's been discussed in this school, right? We have a transversely polarized nucleon, and we're looking at the quark in that nucleon, and we have a correlation between the transverse momentum of that quark and the transverse spin of the nucleon. One can also tackle it in a small x regime, and as was shown by these authors here, Bohr and collaborators and Zhang Zhao and collaborators, one can relate the Sivers function F1T perp at small x to the odderon, and this people came up with coined the term spin-dependent odderon. It's sort of the odderon, the usual QCD odderon, which couples to somehow to the transverse spin of the polarized proton. Okay, I'll switch technical details of how to make this connection under the rug. If this formula is not clear to you, all you have to worry about is always the odderon amplitude. F1T perp is a Sivers function. Odderon is very simply, I always talked about 2 gluon exchanges in the T channel. Odderon is a 3 gluon exchange in the T channel, say between a dipole and dipole scattering. But these 3 gluons have to be in a DABC completely symmetric color state, and this exchange results in in sort of a C-odd. So this triple gluon object carries C-odd quantum numbers, and it's a bit of a mystery. It's a mystery. Okay, these are details don't have the time to discuss. The point is that there is a mystery surrounding the odderon, that the odderon amplitude grows as is a constant of energy. So the power of energy of the odderon amplitude is 0. It's 0 order by order in perturbation theory. There's a general Lagrange argument that it has to be 0. It's 0 at large coupling in the ADS CFT correspondence. So it's some sort of a magical 0. No one really, I don't think, understands why. But the end result, that means that the Sivers, gluon Sivers and quark Sivers functions at small x, because of this odderon exchange, they really behave as 1/x without any power law corrections. One can find a sub-Eikonal correction to it, and Gabe Santiago, who is attending the school, albeit virtually, and myself just last year found this correction. It also turns out to be an integer power of x. So all these integer powers of 1/x, they're integer not because no one tried calculating the order alpha s corrections to the power. It's because those corrections were 0. So it's a bit of a magic thing there. Okay. So in general, one can classify TMDs by Eikonality, how they behave at small x by the power of x. Kind of maybe very remotely similar to classifying operators by their twist. For instance, you can have Eikonal TMDs, which behave as 1/x at small x up to some order alpha s or some such corrections to the power. There are sub-Eikonal TMDs which scale as 1/x to the power 0 as constant at small x. I'll give you some examples now, but the helicity TMDs are one such example. And then there are sub-Eikonal ones which are like Transversity, which go to 0 as x when x goes to 0. So we can talk about Eikonality as this power of x. So, okay, I really don't have any time. I think, Chris, so I'm going to try to round up. Let me just flash that for helicity. One can similarly study helicity TMDs. It's a whole separate discussion. I don't have the time to discuss, but let me just show a summary slide. And there are references there if you guys want to read more on it. So these are, well, these are PDFs, but similarly, helicity TMDs at small x. The grow is 1 over x to some power, and that power is given there here on the right. It's actually not proportional to alpha s, it's proportional to square root of alpha s. That's kind of an interesting feature because there is summation at the leading order is double logarithmic, not single logarithmic. So the expansion of 1 over x, the power of 1 over x is expanded there in the power of the square root of alpha s, not in the powers of alpha s itself. So it's kind of a non-analytic, if you wish, expansion. So you get this for quark and gluon helicity distributions and orbital angular momentum in the Lagrange C. And then if you go beyond the Lagrange C and an F, beyond Lagrange C limit, you consider Lagrange C and an F limit. In addition, interestingly, to this power of x, one gets oscillations with log 1 over x. This is a result that Josh Tawabuter, who is there in the room, I hope, has obtained a couple of years ago. Sub-Eikonal TMD example is the Transversity. Again, let me just show the answer. It's also an expansion in square root of alpha s, non-analytic power, but the expansion is around -1, the power of -1. That means if you plug in the numbers, you get the transversity for valence quarks here going to 0 rather fast as a positive power of x when x goes to 0. Okay, so that's it. I'm sorry for running over. So let me summarize. So I think in this couple of short, well, maybe not very short talks, but in this couple of talks yesterday and today, I hope I gave you at least a sense of what we do at small x. That there's a lot of progress over the last couple of decades plus in small x physics, starting with a quasi-classical approximation with Glauber-Mueller, McLaren-Vinogopoulos model to small x evolution equations, which give us x dependence of many different quantities at small x, which have been rather successful in describing Hera data at small x, and also have had their share of successes in Reed and LHC phenomenology, providing possible evidence for gluon saturation as well. I had no time to discuss phenomenology at all in these two talks. And from the TMD perspective, all this machinery is now being applied to figure out TMDs at small x. From my standpoint, the more exciting TMDs are not the Eikonal ones, but the sub-Eikonal ones and sub-sub-Eikonal ones. There one ends up writing new evolution equations, sometimes with a double logarithmic resummation parameter rather than single logarithmic, which you can solve and find the asymptotics, the small x asymptotics of those TMDs. And hopefully, at least for some of them, when EIC comes online, they'll have enough precision and enough reach and low enough x and enough, by precision, I mean enough statistics because of high luminosity. EIC would be able to measure and verify some or at least several of those predictions. So thank you very much, and I'll stop here.
Thank you, Yuri. Yeah, thanks for covering so much ground and answering questions so willingly. In future school, we'll give you a whole week of lectures. So.
And I'll still run over.
And we'd still learn a lot. Any quick questions from the audience right now? Or from Zoom? While they think about it, feel free to start grabbing coffee.
Last question. Sorry, Yuri, just going back to that picture that you drew in your iPad for the sub-Eikonal quarks that you drew, where you did quark, another quark, another quark. Just one simple question. I think I know the answer, but are those extra dipoles. You drew them in your iPad, I think.
Oh, the iPad. Okay, so it's not about TMDs. Sorry, it was a little hard to hear.
Sorry.
Yeah. Sorry. Let me just go to the iPad.
The topology was very helpful, but just looking at this, sorry, the bottom part, the data. So we're looking at those now head on. Are all those sub-Eikonal quark pairs, are they also with zero transversity?
They're not sub-Eikonal. Sorry, maybe I confused you. This is all Eikonal. So this is a gluon, right? That's a gluon. That's a gluon. So what I drew here is a quark antiquark emitting a gluon. Right. So this was quark, antiquark, and we are emitting a gluon, which is sort of Q and Q bar. And this emission is Eikonal, which means no recoil, nothing, right? We just have a.
So all of those little pairings, they're all equally just in the same direction. There's no transversity to them whatsoever.
Well, I'm sorry, I'm not sure I understand what you mean by transversity.
In terms of the momentum, like when you initially drew these dipoles coming into this thing in the first lecture, right? These quarks are all coming in. This dipole is coming in perfectly in one direction, right, along Z. So all of these little breakoffs are also perfectly along Z, correct? There's no adjustment to their angle.
Right. So let me just clarify, and we'll see if I agree or not. All right. So we have a quark and antiquark forming a dipole. Right. You can work. So of course, say the quark, for instance, has momentum k. Say it's a minus moving photon, right, with some large q minus. K has k minus and k perp, right? K minus we write as zq minus, and it is moving along the z-axis. And there is some k perp. You can even choose initially q perp of the photon 0, right? Then the antiquark, which will carry q minus k, it will have q minus minus k minus and negative k perp, right? So this is 1 minus zq minus, okay, just a different longitudinal momentum fraction. But in transverse momentum, they kind of back to back. But we work in coordinate space. We do a Fourier transform, which is similar, very similar, actually, exactly probably the same as what people do in TMD physics when they go to the B space, to B perp space. And so you Fourier transform, instead of k perp, we get what I was calling x perp. And then the dipole looks like it has a fixed x perp, but it's a two-dimensional Fourier transform, right? The minus momenta remain the same, so we still have z1 minus z fractions. So when I'm drawing this in a transverse plane, I'm kind of working in a x perp plane, right? And I say, okay, there's a quark and there's an antiquark. And this is my dipole in a plane because I'm working in x perp space. It is convenient that they're frozen in this x perp plane. It doesn't mean that they have zero transverse momentum. It just means that their longitudinal momentum is so much larger than the transverse momentum, right? This dipole comes in. Each of these quarks has very large minus momentum, even zq minus, if z is not terribly large, it's very large. It's much larger than k perp, so that for the short time when it goes through the target, the change in transverse position is very small, right? So this is the target, and this is a very short time. So transverse recoil is very, very small and can be neglected. That's why our amplitudes are always diagonal in x perp, right? We have the same x perp here as there. Ultimately, there is, of course, initially the dipole was a point-light object, the photon, right? So, but it does have to evolve into a dipole, and that does, of course, imply that quark and antiquark do have some transverse momenta, which slowly kind of make them drift apart from each other.
Right. So in that region, it's totally Eikonal. In that tiny slice, those things are basically
right. It's all totally Eikonal, and moreover, when I talk about evolution and those additional emissions, maybe that was your initial question. You see, if you emit a gluon like this, for instance, right, you still have kind of a separation of time scale. The time scale before the gluon emission is much longer than the time scale after. I'm not quite drawing it this way. Maybe I should. Let me try to argue this way. So from the standpoint of the original dipole, let me use a different color. This is our target. This is a target at step 0. This is yesterday's discussion. We only have a quark anti-quark dipole, and it interacts with this big target. And then we kind of start renormalizing it, and we say, okay, well, when we look deep inside the target, oh, it turns out that it's not just one big target. We may have this gluon emission, and then we have a smaller target. So this is a target at step 2. But each emission here is still Eikonal. Again, there is no change in x-perp in all those emissions. Change of x-perp happened outside, before and after.
Thank you.
Okay, all right, thanks.
We're gonna let people take the coffee break, but
Very important.
if anyone wants to keep chatting with you. So thank you, Yuri.
Okay, thanks, everyone.
And we'll have you here in person.
I'm sorry, yeah, maybe some other time.
Yes.
So can I leave or somebody has